Hi there, my name's Pete Roos. I'm the president and CEO of Bridger Photonics in Bozeman, Montana. Today I'll be discussing gas mapping LiDAR technology. Our mission is simple: enable clean, safe, and streamlined oil and gas operations by providing actionable data for methane emissions reduction. We created gas mapping LiDAR to make emissions reduction simple. We attach a proprietary laser sensor on the underside of an aircraft to scan oil and gas infrastructure throughout the entire natural gas value chain, from production to transmission to distribution. We currently operate in all the major production basins in the US and Canada. We're used for many PHMSA compliant leak management plans in the transmission sector, many alternative methods to replace ground crews in Canada, and we were recently submitted by ExxonMobil as the first ever alternative means of emissions limitation application to replace ground crews for EPA Quad Away regulatory compliance in the US. We're limited by standing water and snow cover, but we expect the snow cover limitation should be overcome with our Gen 2 sensor coming out later this year. Here's an example of our data products. Our data flows seamlessly into our client's GIS software of choice, and we also provide PDF and spreadsheet formats. We provide aerial photography so our clients know the status of their sites at the time of the scans, and we can identify the equipment on the sites as well. Of course, we provide gas plume imagery, and we use algorithms to backtrack and drop a GPS pin typically within 2 meters of the emission source. We also use proprietary analytics to quantify the emission rates for each of the emissions we find. Finally, while it's not shown here, we can provide an auditable measurement swath that shows our clients exactly what was covered by our laser scan for regulatory or auditing purposes. While this example shows a leak that needs attention, a huge part of our value is showing our clients which sites don't have leaks so that they don't have to visit them with ground crews. This allows our clients' ground crews to focus their efforts where they count, on the emissions. The only way we can make this claim is if we have the detection sensitivity to back it up. So what detection sensitivity do we use and why? For this workshop, I had our team grab data from over 7,000 sites that we scanned in the Permian Basin. The plot shows the percentage of the emissions that we detected on the vertical axis as a function of the sensitivity you need to detect that percentage of emissions on the horizontal axis. We choose a detection sensitivity for the production sector of 3 kilograms per hour with greater than 95% probability of detection, which lies just below this plateau in the emissions distribution. This plateau was previously predicted by theoretical modeling by Adam Brand's group at Stanford and others. We do go more sensitive for the distribution sector, getting down to 0.5 kilograms per hour with 95% probability of detection, assuming unobscured view, by using a detection sensitivity of 3 kilograms per hour with high confidence in the production sector. We catch more than 90% of the emissions in a basin while maintaining a very manageable level of repairs for our clients' existing crews. Moreover, research by Matt Johnson's group at Carleton University has also shown that this sensitivity catches more emissions than ground crews with OGI cameras, but from far fewer emission sources. So gas mapping LiDAR offers a win-win for the industry and for the environment. More emissions reduction with fewer repairs. And finally, our ability to accurately quantify emission rates from the air has become very important for efficiently assessing corporate emissions inventories and for certifying responsibly sourced gas supply chains. Here I'm showing results from a single blind high emission rate quantification study conducted in the Permian Basin. The left plot shows our estimated emissions rate from the air on the vertical axis as a function of the emission rate measured on the ground using a calibrated flow meter on the horizontal axis. You want all the data to fall on the green line. The linear fit coefficients we observe indicate that our estimates from the air are very highly correlated to the actual emission rates on the ground. The same data, plotted on the right, also shows that when we aggregate the total emission rate from all the 72 emitters in random order, as we might expect for an inventory or certification, our estimates from the air come within 4% of the actual aggregated emission rate. However, our white paper on this study describes that single-digit % accuracy is a more reasonable expectation. Well, that's all I have time for right now, so thank you very much for your attention, and please don't hesitate to contact us with any feedback or questions.